Welcome to The Explainer. Today, we're going to demystify the core components powering modern artificial intelligence together. Here's our roadmap: modern language models, algorithm taxonomy, real-world use cases, and Gauss's mathematical foundations. Part 1, Modern AI and LLMs. Let's dig into the architecture behind the generative models you use every day. At their core, it's a massive neural network architecture that powers these models to generate human language. So, how does AI actually use these models? Well, let's break down the 4 structural pillars making it happen. First up, the transformer architecture is the engine. It processes long-range connections across huge text sequences simultaneously. Next, tokenization translates our words into numbers, mapping complex meanings purely through mathematical vector spaces. Then, using probabilistic generation, the model literally just guesses the most likely next word to draft human-like responses. Finally, instruction tuning uses human feedback to make sure those answers actually align with your intent safely. So, what algorithms do these use? Well, deep learning actually sits nested inside broader machine learning. These algorithms cleanly separate into 3 paradigms: supervised learning, unsupervised pattern finding, and reward-based reinforcement learning. And in what cases are they used? Everything from conversational agents and medical imaging to predictive financial analytics. Part 2, Linear Regression and Gauss. Let's explore the foundational 18th century math underlying all this predictive learning. So, how does Gauss relate to AI? Well, he formulated the method of least squares using normal distributions. The real magic here is minimizing those squared residuals to find the absolute perfect line of best fit. This isn't just history, folks. A single-layer linear regression is actually the fundamental artificial neuron used today. That Gaussian assumption provides the mean squared error loss function. This directly optimizes modern neural networks. Beyond deep learning, linear regression itself remains a total powerhouse for practical, high-speed predictive modeling. Because it has such a low computational footprint, it's absolutely perfect for near-instantaneous edge inference. Modern AI just constantly builds upon these classical statistical concepts, scaling them up to process massive datasets. This foundational Gaussian math is what enables modern neural networks to achieve over 100 times the efficiency. I'll leave you with this. What other historical mathematical principles might unlock the next AI revolution?